Hello everyone, welcome back. In this video we're going to talk about planar density. We explained linear density, which represent a density on the directions. Now we will go for planar density, which we will deal with plane, and we're going to find density within a plane. Now, in order to explain, we're going to start the equation that we have it. The equation we have it for planar density says number of atoms centered on a plane over area of plane. So here, since we have plane, we'll take the area of the plane and the number of atoms within the plane. Let's do an example to explain the basics. So let's say we have a simple cubic. We're gonna have a plane which is say 0, 1, 1. Let's go, sorry. Let's make it 0, 1, 1. We're gonna explain same plane for different crystal structure for simple cubic, FCC, BCC, to understand the atom arrangement and the way that we're dealing with plane. So first we will draw the plane. Those are the Miller indices. We're going to convert them to intercepts ABC. 1 over 0 will be infinity. One over 1 will be 1. For C, 1 over 1 will be 1. So those are the intercepts. We're going to use it to draw the plane. This is x-axis. This is y-axis. It's going to be z-axis. So let's specify A, B, C. We don't have A because it's infinity. It's to x-axis, parallel to x-axis. And we have intersection on Z on y-axis. On y-axis is at 1, which will be here the intersection we have it. And intersection with the z-axis is at 1. That's going to be this corner. 1 unit on the z-axis. So we will connect those two together. We'll connect them together, those two. Then since it's parallel to x-axis, we're going to draw two lines at each point. This is parallel to x. And here also we're going to draw a line parallel to x. This is parallel to x. This line are parallel to x. Then we said that we're going to connect the new ends together. That's going to give us the plane which is parallel to x-axis, has intersection at 1 with y and intersection at 1 with z-axis. This is the plane 0, 1, 1. Now drawing the plane, it's independent of the crystal structure. The crystal structure doesn't matter. It's independent of the crystal structure. Well, however, finding the planar density, it requires the crystal structure. Why? Because for planar density, we need the atom arrangement, we need the length of this. Why? Because we're calculating the area, so we need the width and length of this plane. Now, we know that in simple cubic, we have atom at each corner. Now I'm gonna show the possibility. Shall I draw the 4 atoms side by side like this, or shall I draw them in this manner, 2 of them like this touching each other here, and then let's make them a bit bigger. So there is a circle, there is another atom here. Then if there is, or I have to separate them as 4 atom. Now which one represent this plane? Which one represent this plane? Now we have 3 possibilities. Is the first one explaining those 4 atom, or the second one, or third one? By the way, in any of the cases, the plane basically is centered. This is going to be the plane we have it, and this is the plane that we're talking about. Now how do you know which one is the appropriate drawing for the atoms? Well, if you don't have imagination of the crystal structure, there is a way that we can guess which one is it, or we can know which one is it. Now the side of this plane, it's A. We know that this is the cube side, it's A, and A in simple cubit is equal to 2r. Now what does 2r means? It means that the atom are touching, those 2 atoms are touching each other. Why? Because from center to center will be 2r. So it's not going to be this case. Why? Because the atom not touching each other. Yes, this is possible, this is possible. Why? Because this is A, which is equal to 2r. Or here, this is also possible to be A, which is 2r. Now, we'll check the other side. The length of this plane, it's not A. Why? Because this is A and this is A. So if I find this one, will be root 2A. Now since it's root 2A, it means that it's bigger than 2R. Bigger than 2R. So it means that this atom will not touch this atom here. So it's not going to be... Why? Because in this case, it's also A, yes? This is 2R. So it's not going to be this case as well. So which one will be? This is the representation of the atoms in the plane. We have it here. Look, this side is A, and this is going to be root 2A. That's going to be root 2A. That's going to be root 2A. Like this one, if they touch each other, this will be A as well. A will be 2R, but we know that this is not A. This is root 2A. If this side also was A, I would say, okay, the first one is the correct configuration of the way that the atom arrangement we have it. So now we know this is the atom arrangement. We're gonna go to calculate the number of atoms. Now, number of atoms here, you will take what is inside the square, the plane. There's quarter here, there's quarter here, there's quarter here, and a quarter here. So 4 quarter I have it. Number of atoms will be 4 times 1 over 4, because we have 4 corners. So 4 times each corner here will be 1 over 4. 1 over 4. So number of atoms became 1 atom. So when we have 1 atom in this plane, at each corner a quarter comes here. The area that's basically within the plane. Now the area of atoms that's going to be within the plane, that's going to give a number of atom. Quarter here, quarter, quarter, quarter. 4 quarter going to give us 1 atom. Now the area of the plane is A times root 2A. So if I calculate planar density, or write it planar density for this plane 0, 1, 1, it's going to be equal to, those are parentheses, so we said that those are 1 atom, we have it, 1 atom. Then we said planar density of 0, 1, 1 is going to be number of atoms over the area. Area will be root 2a times a will be root 2a squared, so that we have to represent it with respect to r. So whenever I'm asking you represent with respect to r, we know that a is equal to 2r. So if I do this one, squaring this one will be 4. That can be 4r squared. So it's root 2 4r squared. This is the planar density for 0, 1, 1. Leave it like this, it's okay. Now the unit for planar density, because we have r squared, is atom over nanometer square, atom over nanometer square, or you'll take reciprocal, you'll bring this one up, it will be nanometer minus 2. Why? Because it's r squared nanometer minus 2. You can write it in this manner, the unit for planar density. So what we did, we first drew the plane, then we found the length of it, a, root 2a, then we drew the configuration of the atoms, those atoms, we said that because those are touching each other, we have it here, and here because it's root 2a, they will be a bit separated. And we calculate the number of atoms based on the atoms within the plane, so we said that corners will be quarter here, quarter, 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 then the area will be side times, this is length or whatever you call it, side times sides, that's going to be the area, and we have to represent it with respect to r, radius of atoms. Now I'm gonna do the same plane, but this time we're gonna change it to FCC crystal structure. So we're gonna do the same thing, but we're gonna represent it in for FCC crystal structure to see what will happen there. Now when we change it to FCC crystal structure, drawing will still be the same. FCC, the drawing still will be the same. The drawing still will be the same. Why? Because drawing this plane is independent of the crystal structure. So we still have the plane, but A is not equal to 2r here. A is not equal to 2r. We know that in FCC A is equal to root 2r. A 2 root 2r. A is equal to 2 root 2r. We know this one from there. Now, since we have FCC crystal structure, we still have atoms at the corner, yes, atoms at the corner, but also we have atom at the face, because this is at the face and this at the face, so we have atom at the face as well. Now, if we go for the atom arrangement to see we have those atoms within the plane, so how I'm going to draw? There's 3 here, 3 here, so I'm going to draw some possibility. Let's say the first possible case, oops, I think I lost everything. FCC. Now we said that we have also 1 here, 1 here. Now, the first possible case, I will draw the atoms touching each other, and there will be another one will be here. I think I'll draw this one somewhere else. let me just sorry for that, just to create the things a bit nicer. I'll try to do it in this manner. So the plane that we had, it was something starting the plane that we have it, something like this. Okay, this is the plane that we have it, and we said that the atoms that we said that we had atom at this corner here, and then atom at the other corner as well. We have it. So atom at this corner. We're doing it for what? For FCC. So those are the location of the atoms. We have them, and we said also we have one at this face, one at this face as well here. We said this was A here, and this side is root to A. So this is FCC crystal structure, and the plane that we have it is still 0, 1, 1, 0, 1, 1, 0, 1, 1, and we know that A is equal to 2 root 2R. So we say when we come to drawing the atoms arrangement, so we have some possibility. I can do it in this manner. So we have the 3 atoms are touching each other. And also the one at the bottom, they will touch them. This is one possibility, we have it here, one possibility. The other possibility that we may have it, it's the top one. So we may have them touching each other. Let's draw the other possibilities to see which one will be the case that we have it here. So this time we're just going to separate a bit in this direction, and the last one that we have it will be all separated in a way that going to come something like this manner. So which one is going to be the possible case? We will realize that if you don't know how to get the possible case here, which one is the possible case, we said that we're going to check the side of the side of the plane. Now we have A here. A in case of FCC is 2 root 2R. So it means that they are not going to touch. I mean, this is, we call it A, yes. This is the side which is A. This is going to be the A. And this is the side which is root to A. Now A, it's 2 root 2r, so it's more than 2r. Why? Because the first case, when they're touching each other, this is 2r, yes? Well, A is not 2r, is 2 root 2r, so it's not the first case. Those two atoms here, they are not touching each other, so it's not the first case. Yeah, this is possible. Why? Because it's more than 2r, more than 2r. One of these two possibility I have it. One of those two will be correct. Now, going to the other side, this is root 2a. Root 2a, we have it here, root 2a. Now, is root 2a, is it going to be this one or this one? Now, why? Because from here till here, if I check this, so how much will be? Will be r here, 2r here, 1r here, this is 4r here. In this case, this is 4r here. Now, is this equal to 4? Because this is root 2a, yes? This length is root 2a. Is this equal to 4r? Is this equal to 4r? We'll check. Why? Because we have 2 root 2 times root 2, because root 2 times root 2 will be 2, 2 times 2 will be 4. That means it is 4r. Well, if this distance 4r, it has to be this configuration. Why? Because the atoms are touching each other in the diagonal, and we already know this one from FCC. The diagonal are touching each other. Well, if you remember it from FCC crystal structure, like this is the diagonal, it's the diagonal, they're touching, the atoms touching on the diagonal, but this one is not touching the one, the corners, those are, the edge are not touching each other. So we got the configuration. This is the configuration, we have it. So we will go and try to draw the plane that we have it. This is going to be the plane. Then number of atom, the corners, we have 1/4. So we have 4 1/4, we have it. But those are half. Those are half. So 2 half and 4/4, we have it. So 4/4 and 2 half we have, which is going to be 2 atoms. Going to be 2 atoms. Well, we can go and calculate a planar density, because planar density will be equal to number of atom over the area. Area will be what? A times root 2a. That's going to be the same thing, yes, root 2a square, but a here is different. A here is different, so you're going to represent a as root 2 root 2r, which is going to give us, this is root 2, we have it here, and we know that this is 2 root 2 r square. We can leave it like this, or we can simplify it more. That's the planar density for 011 in FCC crystal structure. So you realize that by changing the crystal structure, the atom arrangement will change, and also the dimension is still a root 2a, but because a is going to change, also the area is going to change. Now let's do this one, the same thing for BCC crystal structure. If I change this one to BCC crystal structure, so we're going to make it another video, not to be long. We're going to do the same thing with BCC crystal structure. Thanks for watching.